Okay, so we're going to be talking about acceleration now. And if I ask you just in your own words, forget about stuff on the board behind me, in your own words to tell me what acceleration is. Jeff, what would you say?
It's accelerating.
Which means doing what?
Speeding up.
Speeding up. And the opposite of that would be?
Slowing down.
Which is called deceleration. So we're going to look at both of those. But instead of just saying they are accelerating or they are decelerating, we're going to actually put a number on that. And I want you to know how we arrive at that number and what it really is saying, what it's describing. I need you to put your notebooks away and your pens and all the stuff you're using to draw on your notebooks so I can have your full attention. Okay? What I'm going to describe today, you're going to be using for the next several days. It's the main concept, so I won't try to go on longer than necessary, make this too painful. Let's just say that my acceleration right now, I'm going to give you a number, is 0. Am I going very fast? No. Am I going very slow? No. So what am I going? Okay, well let's not say it's me. Let's say the car's acceleration out there is 0. Describe the car's motion. Nathan. Well spoken. He said, no matter how fast it's going the same. Does that tell you the car's speed? No. Could that car be going really fast and have an acceleration of 0? Yeah. Could it be going really slow and have an acceleration of 0? Yes. Could it be stopped and have an acceleration of 0? Yes. Yes. Okay, so do you see how the two are not the same? Speed and acceleration are two different things. Speed describes how far you travel in a certain amount of time. Acceleration describes how your speed is changing, if it's going up or if it's going down. Okay? And if we were to put a math formula on it, it would look like this. Acceleration is change in speed over time. You talk about changing speed. The question is, how much time does it take for that speed to change? And if you look at my fancy-dancy formula up here, you'll see how this all works out. Okay? It's VF minus VI divided by T. VF is the final speed. VI is the starting speed. And T is the time it took to make that change. And I've tried to illustrate it here for you. We're going to do a couple examples, and hopefully when I'm done with this, you'll understand. So we've got this dude. He's carrying the torch, the Olympic torch. He has some starting speed, whatever it is, and then he starts running, let's say, faster. He increases his speed, goes by faster. If we want to know how much he accelerated, you need to say, during what time period? From here to here, for instance. Let's say that was 5 seconds. I need to know what was his speed here, what's his speed at the end, and how much time did it take to change the speed. Let me use myself as an example. I'm going to start over here on this side of the room. And right now, what is my speed? 0. Okay, because I'm stopped. I'm going to keep this real simple. Then we'll do some other examples. And I'm going to gradually accelerate, and I'm going to reach my top speed over here on the other side of the room is 5 meters per second. Okay? It took me 5 seconds to reach that speed. Can anyone tell me what my acceleration is? Zach? 1 what?
1 meter per second. I have no idea.
You're very close, Nathan. 1 meter per second. Okay. Now, let's just look at this. Let's go back to what we do know. You all remember this, right? Speed equals distance divided by time. How many things do you need to know to find speed? 2 things. Okay. Now, that formula over there says acceleration is final speed minus starting speed divided by time. In my example, how many things do you have to know to solve acceleration? 1, 2, 3 things. We'll get back to that in a little bit. So my final speed over there when I was done speeding up was what? 5 meters per second. I'm going to put the label on here because that becomes important. My starting speed back here was 0. You got to put it in the right order. And the time it took me to reach that final speed was 5 seconds. All right. So now we know that this is the same units as this. So we could just do straight subtraction. And the answer, of course, is 5 meters per second. Okay, I can subtract them because they're the same units. And then the number on the bottom is 5 seconds. That's still the same. Now, I can divide numbers. That's not a problem. I can't divide seconds into meters per second because they're different units. You do understand that, right? But what I can do is I can divide the number. 5 goes into 5 once. And the label then on my answer for acceleration would be 1 meter per second per second. That's kind of unusual, something different that you haven't seen before. Remember, how many things went into finding acceleration? 1, 2, 3. How many things do I have on my label? 3. 1, 2, 3. 3 parts to my label. If this were a speed label, like 1 meter per second, there's 2 parts to it. Okay? But you have 3 parts if it's an acceleration. And here's how I would read this. So that it isn't just a number with some weird label. So you understand what this is saying. What this is saying is there's a speed part and a time part. Remember, this is change in speed over time. So I have a speed part up here and a time part at the bottom. What this number is saying, I would read it this way. I would say that every second I'm going to go this much faster. That's how this describes my change in speed. Every second I'm going to go 1 meter per second faster. Okay? In 5 seconds, I was going 5 meters per second. How fast would I be going at the end of 6 seconds if I continued like that? And 7 seconds. 7 meters per second. Do you see that? It's saying every second I go this much faster. How many understand that so far? Okay. Head up, please, Anthony. Now, there is a shorthand way of writing that. Some of you may have guessed this already. 1 meter per second squared. This is how you can look at it. Just consider that I have this per second twice, right? There it is. You get it? That's the same as saying 1 meter per second per second. And we just say it's 1 meter per second squared is my label. 1 meter per second squared. And you can do that whenever you get a number like that. 1 meter per second per second. You can always write it and should write it like that. Now, let's do some other examples. Change up some numbers here. Let's say, I kept this really simple. Let's say that instead of being 0, that I was actually doing something. That I'd been running before I reached this point right here. And I was going 2 meters per second. So I was already going 2 meters per second when I hit this point. Boom, now I sped up to 5. How much did my speed increase by? 3. 5 minus 2 is 3 meters per second. And how much time did it take me to increase to that? 5 seconds. That's still the same. Somebody want to tell me the answer there? 3 divided by 5? 0.6 what?
0.6 meters per second.
Good. I could write it as meters per second or meters per second squared. And that's how we're going to do it. So again, what this is saying, Rochelle, is that every second I'm going this much faster. I am still speeding up. Not as much as I was before. Do you see that? Every second I'm only going to increase by this much, but I am still speeding up. Let's do another example. Let's say now that at the beginning of this whole business, I was going 7 meters per second. That is my starting speed. I was already going 7. I hit that mark, boom, you start the time. 1001, 1002, 1003, 1004, 1005. I slowed down over that 5 seconds. You see that? My starting speed is less than my final speed. What's the number up here going to be? Negative what? Negative 2 meters per second. My speed went down by 2 meters per second. Whenever you see that minus sign, that tells you we're talking about a what? Decrease. What's the name for the decrease in speed? Deceleration. 2 divided by 5 is? 0.4. And it is a negative number. Negative 0.4. What's the label? Not ms squared. Meters per second squared. So that means every second I'm going to go this much slower. I'm going to decrease my speed by that much. Okay? Whenever you get a negative number, that means deceleration. All right, one more example. Let's just say, we'll go back to my original one here, that I was going 0 at the beginning. I was stopped. 0 at the beginning. And it took me not 5 seconds, but 5 hours. Someone tell me the answer now. Zach?
It would be 1 meter per second per hour.
Excellent. Now, this again is confusing to people because they think, you said that I can't divide apples and oranges. How do I do this? I mean, if this comes out to 5 meters per second and I have 5 hours here, how is it that I can divide that? Well, here's how you can do it. I can divide that because this never goes away. This is still in my label. Do you see that? It's still divided by hours. But the numbers I can divide. And it's still meters per second per hour. It's meters per second divided by hours. I just left the label there. If you get that kind of a problem where this unit is different than this unit, you can go ahead and do your division. Just make sure that that is in your label. It's saying now that every hour I'm going to increase my speed by this much. You get it? I still am speeding up, but it's very gradual. Every hour I'm going to go this much faster instead of every second. How many feel comfortable with using this formula now? Good. So you should know now what the positive versus the negative numbers mean and how to label your answer, what that's actually saying. Now, graphing. Graphing's a whole nother story. What kind of graph is this?
A line.
Yeah, it's a line graph, but what is it showing me? Car race what? What about the car race is it showing me? I heard someone say it, acceleration. It's not a speed graph. And that, I know, can be really confusing to you guys because you're thinking, but it says speed right there. If this were a speed graph, it would have time here and what would be over there? Distance. Speed is distance compared to time. How does your distance traveled change over time? An acceleration graph compares your change in speed to time. Okay? So this is an acceleration graph, but let's just quickly review how the two are different. Tell me now, on a speed graph, Matt, I'm going to pick on you again. On a speed graph, what does a steep line indicate?
That it's getting faster.
That they're going fast. A steeper line means you're going faster than a more flattish line, right? If the line is completely flat and it's a speed graph, what does that indicate?
That it's going at the same speed.
Bianca? What does that indicate when the line is flat on a speed graph? We just did that on our homework. That it stopped. Andrew, what does it mean when it's going down?
They're going down in speed.
No, this is a speed graph, not an acceleration graph. When the line's going down, remember, what's going to be over here on the speed graph? Distance. So if the line's going down, what does that tell me about my motion? What did it tell you about the skateboarder's motion? Let's just say this was distance in kilometers. 64 kilometers, 48 kilometers, 32 kilometers. What's happening? Jeff?
It's going backwards.
It's going backwards. We're losing distance, okay? Now all bets are off when we're talking about an acceleration graph. Those lines mean something totally different when it's acceleration. Now it's not distance over here, it's speed. As we look at an acceleration graph, the steeper the line, the greater the acceleration. Doesn't mean they're going at a faster speed, it means that they're speeding up more. They're increasing by more, okay? The steeper the line, the greater the acceleration. If the line is flat, what does that indicate about the car?
It's going at a
Constant speed, not stop. See, look at this, like this red one here. Once it reaches this point, this is a constant speed, 64 kilometers per hour. And it continues at that constant speed all the way across. If it goes down on an acceleration graph like you see here, what does that tell you? Deceleration. We're slowing down. We're losing speed over time. It's not the same as a speed graph. A downward line would mean going backwards. Here it means we're losing speed over time. All right, so I'm going to ask you to interpret a graph very similar to this as part of your in-class and homework assignment. And I'm going to ask some specific questions. And I want to go through that with this example because I think once you understand on this one, you'll do fine on the homework. First of all, when you look at the graph, it's not set up like the like the one I had you guys do the other day. It's set up with blocks. Every 2 blocks are 5. Yours were every block was worth 1. Remember that? So 1 block, 2 blocks is 5. 1 block, 2 blocks is 10. So what would this halfway point right here be? 2.5. What would this then be? 7.5. And here? 12.5. And here? 17.5. So you have to be able to read in between and know what those are worth. Are these worth 2.5 going up? If this is 16, halfway would be 8. And then add 8 to 16, you get 32 plus 8 is 40. I thought I heard 44 out there, okay? So you keep adding 8 going up. The other thing to understand is that when you're looking at a graph like this, you cannot say what is happening off the graph. For instance, tell me the speed of car C, Mitchell, at 36 seconds. Car C is the red one here. Tell me the speed of car C at 36 seconds. You can't. Remember, I just said, you can't tell me anything that's not on the graph. At 36 seconds, which would be up in here somewhere, there's no line. I could guess that that line continues straight out, just like I could guess that this line goes up. But I don't know. It's not on the graph. So when I ask you questions about a graph line, all you can talk about is what you can see on that graph. Melissa, what is car B's speed at 36 seconds? Can't tell. What's its speed at 35 seconds? Car B's speed at 35 seconds. 0. At that moment in time, we know it's at 0. Whether or not they took off and started going again, I don't know. It's not on the graph. All right, let's try some other questions here. Tell me, car A, when was car A's acceleration the greatest, TJ? Car A, when was their acceleration the greatest? No, that is when their speed was the greatest. Remember that the line tells me about acceleration. The steeper the line, the greater the acceleration. Nathan? So between what and what? Excellent. Between 0 and 7.5 seconds. Here's 7.5 right here. We should have looked for the steepest line. You see the green part? You've got this part, you got this part, and you got this part. Wherever the line is the steepest is when we are accelerating the most. I didn't ask you when they were going the fastest. That was up here. Okay? I asked you when they were accelerating the most. And that was between 0 and 7.5 seconds. What is car A's speed at 7.5 seconds, Sky? Car A's speed at 7.5 seconds. So you go over to 7.5 up until you hit the line. What's its speed? 56. It was 48 plus 8. That's what this one is worth. 56 right there. 56 what? What's the label? Kilometers per hour. You got it. Okay, good. Now, a couple more questions, and then we'll be done here, and I'll give you your version of this. If I had to put these three cars, A, B, and C, into one of three groups, either they are reckless, they stalled, or they were a safe driver. Which of these three cars, based on what you see graphed up here, would you say is the one that stalled? Their engine died into the race. Zach?
Car B.
Car B stalled?
Yeah.
Okay, because it goes up and then it falls down gradually. Do you see it takes, what, 25 seconds for it to go from this speed down to 0. 25 seconds. That didn't happen all of a sudden. So we would say car B stalled. Which of the two cars left would you then say was the reckless driver? Andrew? A. Because A went and accelerated and kept changing their speeds. They're probably the better race car driver, but it is more reckless because they accelerated and kept changing speeds. So that makes A our reckless driver, and then of course our safe driver would have to be C. So when A, B, C in that order. C was like a good driver, steadily accelerated, didn't floor it, reached their top speed, and maintained it. Jeff, you had a question?
No,
Just stretching? Okay. Now the last question, this requires a little bit of thought. I had to think about this myself. And I was quite proud of myself when I figured it out. I was thinking, man, I wonder if by looking at an acceleration graph like this, if you could figure out who won the race. Because it's showing me changes in speed over time. Now let's assume that the race ended here at 35 seconds. You might immediately assume, well, the blue car is out because they were at 0 at the end of the race. Not necessarily. You may immediately pick the car that was going the fastest at the end of the race. Well, can you imagine a situation where we're racing in cars and at the very end you're going faster than me but I won? If I was going faster than you the rest of the race and at the very end you sped up, I could still be way ahead of you. You see what I mean? It's like you're racing someone around a track and at the very end they make a surge but they're so far behind that they still can't catch you. Then it occurred to me that the winner of this race is the person who traveled the fastest for the longest amount of time. Does that make sense? The person who traveled the fastest for the longest amount of time. Based on that, how many of you think car A won the race? How many think car B won the race? How many think C won the race? Interesting. Okay. Well, I said the winner is the one that traveled the fastest for the longest period of time. Let's just make this a little more obvious. Let's say that another car, we'll call it car D, accelerated like this. Which car would you say won the race now?
D.
D. Pretty obvious, right? Because at every moment in time, car D was going faster than the other three cars. You see that, right? Well, look at how the line looks. Now, I'm going to ask you one more time. How many think, forget about D now, how many think car A won the race? How many think B won the race? And C? Okay. Right off the bat, you should be able to throw C out. You can see that car A beat C clearly. For every moment in time, this line is higher up. They're going faster every moment in time than this one. Well, think about that, guys. If we head out on our race and I'm always going faster than you the entire time, how is it possible that you could win? You see what I mean? So C's out. So the only ones we have left to compare would be A and B. And the answer is in the space under the line. That big line, did you see how it contained the other two? Okay, I was going faster the entire time. If you look, this is why graphing is so useful. Simply by graphing this, I can look at the graph and I can tell you who won the race. I look at the area under the line. Think of these as three different houses. A red house with all of this space here, a blue house with all of this space in here, and a green house with all of this space. Now can you tell which one won? Well, look at the blue house. The blue house has all of this stuff in here that's above the green, right? So all of that is more than the green. But look at what the green has over the blue. All of this in here is faster than the blue. So during all of this time, they're going faster than the blue. Well, now what would you say? Blue or green won? Green. Green was going faster for more of the race than the blue. Yeah, at some point in time, blue was going faster than green ever went. But it was a short period of time, and then they lost their speed. So by looking at the space underneath the graph line, you can tell who won. Yes?
Couldn't the green car come off track or something maybe the constant speed?
You're right. That's true. We don't know. We're assuming that all this speed gain was on the track. That is true. This is going to require a little explanation too. So just wait. Get your name, date, and period on the top. Okay, this is called the car race, just like this one. The lines are very similar. Same kinds of things you'll have to do. First of all, I need you to correct a little typo. Right here where it says speed, km/h, it should say km/hr. It should be hours, and it's not abbreviated with an H. And it says here at the top, it says, the graph below represents 3 cars during the first minute of a race. Using this information right here, you're going to draw another line for car D. And you're going to add car D to your graph. So like right down here, if you got a blue pen or something, you can put D, and then you graph whatever they tell you that line does. Okay? Then you're going to use all 4 of those graphed lines to answer the questions below. When you answer these questions, only these guys are excluded from the complete sentence rule. All the rest of these should be in complete sentences. It may be very short, but they should be in complete sentences. Questions?